All right, so let's get started. So hopefully more people join later. Okay, so today we're moving on to a different topic. So we're talking about lower bounds now. Okay, so did you guys watch the video? Any questions about any parts of the video? All right. So the reason why lower bounds are interesting is one reason is that whenever you can prove a lower bound, then so usually we want to design algorithms, right? So algorithms are the things that let us solve a problem. So one second, I need to just. Yeah, okay, sorry about that. There's a lot of noise coming through my window. Okay, so the reason we care about lower bounds is that well, usually we want to have algorithms. Okay, algorithms let you solve a problem, whereas a lower bound says that you cannot solve a problem, or at least you cannot solve it very efficiently, or something. Okay, so why would we be interested in lower bounds, right? Why do we want to know what we cannot do? Well, the reason is that, for example, if you design an algorithm, okay, and it has a certain complexity, then okay. In terms of registration, I don't really care about the registration. I mean, if you guys want to do that, that's fine. Yeah, that doesn't matter to me. Okay. Um, okay. So the reason we care about these lower bounds is because if you have an algorithm, right, then you want to know whether you should keep trying to improve that algorithm. Okay. So if you have a lower bound and you have an algorithm which can match your lower bound. Okay, so let's say that you have a sorting algorithm, right, which runs in time, let's say n log n time. Okay, now you might be wondering, should I try to improve this algorithm, right? Should I try to get a linear time sorting algorithm? Okay, but if it turns out that you can prove a lower bound, right, of let's say n log n, right, then that tells you that this algorithm that you currently have is the best possible thing. Okay, there's no point trying to improve this algorithm anymore. Okay, so one reason lower bounds are interesting is because it tells you when you can stop as an algorithm designer. Okay. Also, lower bounds, if you can manage to prove a lower bound, you can often find out like the core part of the problem, which is difficult. Okay, because when you design one of these lower bounds, you're usually trying to show that there's one part of this problem which takes a long time to solve. Okay. And that also tells you as an algorithm designer where to focus your efforts, okay? Because you've identified like the hardest part of this problem, okay? So then when you're designing an algorithm, you can also try to just make this hard part work as efficiently as possible. Okay, so yeah, so there are lots of reasons to be interested in lower bounds, and also lower bounds are just sort of interesting from a theoretical point of view, right? I mean, you have to work pretty hard to prove these lower bounds, and they're just kind of an interesting sort of academic thing to do. Okay, now we actually do not have lots of lower bounds in computer science. Okay, we have lower bounds for some simple problems like the ones I'm going to talk about today, and of course we have more sophisticated lower bounds. Okay? But for the really interesting problems, we don't really have any useful lower bounds. Okay, so for example, for these NP-complete problems, okay, what we suspect is that they take more than polynomial time, right? They might require exponential time to solve. Okay, so ideally, we would like to prove that these algorithms take, for any polynomial, right, you have a lower bound, which is at least that polynomial for an NP-complete problem. Okay, however, we're very, very far away from being able to do that because currently I think the best lower bounds for NP-complete problems might be just sort of linear time. Okay, so I'm not like a big expert on this, but I believe that we have very, very weak lower bounds for NP-complete problems. Okay, so let's say that we have a linear time lower bound. Okay, and then for the upper bounds, which are the algorithms to solve these NP-complete problems, we have like exponential time algorithms. Okay, so there's a huge gap between the lower bound, which is like linear time. Okay, so you're saying it takes at least n time to solve the traveling salesman problem, right? Whereas for the algorithms that we have, right, they might take something like 2 to the n time. Okay, so there's a big gap between what we can prove for the lower bounds and what we have for the algorithms. Okay, and yeah, so that's the situation, and we don't have any better techniques to prove these lower bounds. So it looks like, for the time being, we are not going to be getting anywhere close to the to sort of making the lower bound and the upper bound be tight for these NP-complete problems. All right. Okay, so yeah, so that's sort of some basic introduction to this stuff. And now so the types of arguments that we're going to use today for the simple lower bounds that we're going to talk about. Okay, so they're basically called an adversary type argument. So what you're doing is that you're creating a particular input that forces the algorithm to run for a long time. Okay, so you can think of yourself as an adversary to the algorithm. Right? The algorithm is trying to solve the problem as efficiently as possible, and you're trying to like defeat the algorithm and make it not be able to solve the problem quickly. Okay. All right. So these adversary algorithms often work by using this indistinguishability argument. So this means that we're going to create like two inputs. Okay, and then so we let the algorithm do anything it wants on the first input. So call these x and y. Okay, so the algorithm can do anything it wants on the input x, right? Because we don't put any restrictions on the algorithm. Okay. However, then we're going to argue that for this other input y, right, it's somehow indistinguishable to the first input x. Okay, and what we mean by indistinguishable is that the algorithm can't tell any difference between x and y. And the reason it cannot tell any difference is because, if the algorithm runs very quickly, then x and y might just differ in like one tiny part of their inputs. Okay, so x can be like a big input, y can be a big input, and they can differ maybe they differ in just one small part. So if the algorithm runs very quickly, then it simply won't see that small part. Okay, and in that case, since it can't tell any difference between x and y, and so it's going to behave the same on x and y, right? And then also for these two inputs, for input x, the algorithm should output one answer, and then we're going to ensure that for input y, it should output a different answer. Okay, but now because the algorithm can't distinguish between x and y, it's actually going to output the same answer on both x and y. And that means that the algorithm is incorrect. Okay. And so that shows that this algorithm cannot run very, very quickly, because if it runs too quickly, it's not going to see the difference between x and y, so it's going to output the same, it's going to produce the same output, which is incorrect. Okay, so that's the basic idea. Does that make sense for everyone? Okay. Now, also these lower bounds are very sensitive to the type of model that you work in. Okay, so I mentioned this in the lecture, but for example, today we're going to prove a lower bound for sorting. Okay, and the model we're going to use is this thing called a comparison-based model, where the algorithm can only compare two input values. Okay, and then based on whichever one is larger, it can make additional decisions. But basically, it can only do these comparisons. And in that model, you can show that you need to make at least n log n comparisons to sort n numbers. Okay. However, if you're in a different model, then you can actually sort more efficiently. Okay, so if you're allowed to do more than just compare two numbers. So for example, if you can look at the individual digits of these numbers, okay, and let's say that you can do arithmetic operations on them. So you can add two inputs or multiply two inputs. Okay, in that case, we can actually, we have some algorithms that can sort faster than n log n time. Okay, so can you guys think of any algorithms that can sort in linear time? Okay, if you have n inputs, okay, any algorithms that you know of that can sort in order n time. Okay, radix sort, yeah. Any other algorithms? Merge sort. Why do you say that? So you think merge sort can actually run in linear time? Well, I mean the merge. The merge algorithm. Okay, right. But I'm talking about like a complete sorting algorithm. Okay, right. I mean for merge, that's not going to sort n values, right? That's only going to merge two already sorted lists. Right. Okay. Yeah. Sure. And then bucket sort. Okay. Or something which is similar to bucket sort, which is counting sort. Okay. Yeah. So the first sorting algorithm is like radix sort. And if you guys remember how that worked, so that is sorting a bunch of numbers. It's going digit by digit. Okay. So if you have and then for each digit, so let's say that you have n numbers. Okay. So for each digit, you're going to spend order n time. Right? And then if you have, let's say, 32-bit numbers, okay, so that's 32 digits, then the entire writing time is just going to be 32 times n, okay, order 32n. Okay, so in general, if you have like if you have k digits, then the running time is going to be order k times n. Okay, so if k is a constant, then this is running in linear time. All right, and then for bucket sort, so there's something very similar to bucket sort, which is called counting sort. So I'll just describe the counting sort algorithm. So basically, for counting sort, you're given like n numbers, but you have a bound on how big these numbers are. Okay, so let's say all the numbers are between like 0 to 100. Okay, so then in that case, you're just going to make an array of size 100, or let's say 101. Okay, 101. All right, and then you're just going to go through your array of n numbers, and then for each one, right, it's going to be a number from 0 to 100. And so in the array that you created, you're just going to keep a count of how many copies of each number you've seen. Okay, so if you see a 3, right, you're going to increment the counter for 3. Okay, and then if you see like a 5, you're going to increment the counter for 5. Okay, so then you just sweep through all of your n numbers once. Right, that's going to take you order n time, and for each one of these inputs, you're just going to increment one of these counters in your array. Right, and then in the end, after you've done this for all your inputs, right, you just go through your array once. Okay, so if your array has like 101 elements, you just sweep through this array, and you just look at how many copies of 0 there are, right? How many copies of 1, how many copies of 2, and so on, up to 100. Okay, because you know all the values are between 0 to 100. Okay, so this way, and then you have to just output those numbers, right? So if you see like 3 zeros, you're going to output 0, 0, 0. Okay, and then if you saw like 2 ones, you're going to output 1, 1. Okay, and so on, right? So you're going to sweep through your array once, and then you're just going to output all of these numbers. Okay, so therefore, if you have n input values to start with, right, and if all the values are between, let's say, 0 to m, okay, some sort of value m, then the complexity for this algorithm is just order n plus m, right? Because you have to sweep through your n numbers once to get the counts, and then after that you have to sweep through your array once, right, which has size m, to output all the values. Okay, so both of and then if m is small, then again this is going to be a linear time sorting algorithm. Okay, so both of these algorithms are well, they're going to be linear time given certain assumptions on the input, right? And so they actually do not follow this lower bound. Okay, but the reason they don't follow this lower bound is because we're not in radix sort and in counting sort, we're not just comparing the values, we're actually looking at what the values are. Right, like for example, in radix sort, you actually need to look at every individual digit of the inputs, right, and be able to compare those digits. Okay, and then in counting sort, you're actually looking at the values themselves, right? You don't just compare two values to see which one is larger. you need to see what the actual value is, so you know which entry in the array to increment. All right. So the point of all this is that you have to be careful about the model that you work in, and the weaker your model, the easier it is to prove a large lower bound in that model. Okay, so let's see. Oh, right. And also, some of these lower bounds are only worst case lower bounds. Okay, so what they show is that if you want to solve this problem, then no matter what algorithm you use, there is some input for that problem where you have to take a lot of time. Okay, it doesn't show that for every input you need to take a lot of time. Okay. You can also prove other types of lower bounds. So for example, for this sorting lower bound, right, for this n log n lower bound, you can actually show that this is an average case lower bound, meaning that if you get like n random numbers, okay, then on average, your algorithm is going to take n log n time. Okay, it's not just one particular input that makes it take n log n time. It's sort of like if you get like a random sequence of inputs, it's going to take n log n time. Okay, but usually we're going to prove worst case lower bounds. All right. Okay. So yeah. So we have this lower bound for merging two lists. Okay. So any questions about how this one works? When the two list size n are sorted, why is the upper bound for sorting them into a sorted list 2n? Oh, all right. So this is actually the merge algorithm that Jiahui was talking about, right? So if you have two lists of size n, then you keep a pointer for each one, right? And then the pointer starts at the beginning of both lists, and then it moves towards the end of both lists. Okay. So the pointers point to two values. Yeah, it's 2n minus 1, right? Yeah, it's n plus n minus 1, yeah, right? So the two pointers point to two values, and then you have to compare them, and then whichever one is like, let's say smaller, right, you're going to put that into the output list. Okay, so the two pointers have to go all the way to the end, right? And so whether we should prove the upper bound at the beginning. Okay, well, it depends on what you're doing. So if you want to show that the lower bound is tight, right, then you after you prove your lower bound, you also have to give an upper bound which has the same complexity. Okay, but if you're just trying to prove the lower bound, then you don't care about the upper bound. Okay, so in this case we have a tight lower bound, right? It takes at most 2n minus 1 comparisons, and then also we have this example where it takes at least 2n minus 1 comparisons. Okay, yeah. And that's good because that both tells you that you don't need to look for a more efficient algorithm, right? Because it's already matching the lower bound. And also you don't need to prove a better lower bound because there's already a matching algorithm. Okay, so once you get that tightness, then you can stop. Okay, so any questions about how we created this example of this merging example? Right, so what we're showing is that on this particular example, okay, where you have these two interleaved sequences, right? So A is the A sequence is already is completely sorted, right? And the B sequence is sorted, right? And then these two things like interleave with each other. Okay. Then for this particular input, you have to take at least 2n minus 1 comparisons. Right? Because you need to do, so we have these, two types of, what's happening here? Yeah, so we have these two types of comparisons, right? The AI and BI comparisons, right? So we show that you have to do every one of these comparisons. Okay, and so that's n comparisons right there. And then we also have these other comparisons, the BI with the AI plus 1. Okay, and we show that you have to do all those comparisons. So that is going to be n minus 1 comparisons. So altogether, that's 2n minus 1 comparisons. Okay, any questions why these two claims are true? Okay, so let me ask you guys a question. So we showed that you have to do these two types of comparisons, right? AI, BI, and then BI, and then AI plus 1, right? Now, can we show other types of comparisons that you have to do? So for example, suppose I want to show that you have to compare, let's say, A1 with B3. Okay, so suppose I want to prove this. Okay, now this is actually not true. Okay, for a merging algorithm, it does not have to prove compare A1 to B3. Okay, but why not? Right? Why can we show that the algorithm has to compare AI and BI, but we cannot show that it has to compare, let's say, AI and then BI plus 2? Any thoughts? All right. Well, the basic idea is that once the algorithm does transitivity, okay, yeah, excellent. Okay, so let me just expand a bit on what Zihao is saying. So the idea is that once the algorithm does some comparisons, okay, then it can combine all the information from all of those comparisons using transitivity, okay, to get some sort of implied comparisons. Okay, so what I mean by that is, suppose the algorithm, suppose we're trying to show that, suppose we're trying to force the algorithm to compare A1 and B3. Okay, now the reason the algorithm doesn't have to do that is, for example, if it compared A2 to B2. Okay, and let's say that, so in that case, it's going to see that A2 is less than B2, right? And then the algorithm knows that because it's given a sorted input, it knows that A1 is less than A2. And it also knows that B2 is less than B3. So therefore, once the algorithm compares A2 and B2, and it learns that A2 is less than B2, then by transitivity, it also knows that A1 is less than B3. Okay, so therefore the algorithm is not going to do that comparison anymore. Okay, but the reason it must compare A2 to B2 is that there's no transitive relationship that can tell the algorithm which one, A2 or B2, is larger. So for example, if the algorithm compared A1 to B1, okay, and it also compared A3 to B3, okay, so even after those two comparisons, these two comparisons do not give the algorithm any information about whether A2 is larger than B2. Right? There's nothing. There's no sort of transitive relationship that A1 B1 and A3 B3 have on A2 B2. Okay, so that's why the algorithm needs to do all of these AI BI comparisons. Okay, because there's no transitivity that it can use, but it doesn't have to do these comparisons between values that sort of differ in more than one index, because it can use these transitive relationships. Okay. All right. So let's see. What I think we're gonna yeah. I think I asked you guys to watch the video up to the merge part, right? Is that correct? Now, before we actually start the video portion, okay? So I just want to so in this lecture we talked about the time complexity to find the max of a list, right? To find the max value of a list, okay? So I just want to like sort of touch on another problem, which is now what's the complexity to finding the second largest value in a list? Okay, what do you guys think? So to find the largest, it's pretty easy, right? You just keep track of, you go through all the elements and then you keep track of what you think is the largest, okay? The largest value that you've seen. But what about the complexity to find the second largest value? Can anyone propose an algorithm to do that? To find the second largest value in a list? So first of all, so let's sort of, let me give you a hint. Can you try to use divide and conquer to try to find the second largest value? Keep track of both the largest. Okay. All right. So if I understand correctly what you're saying, yeah. So suppose you have a oops. Let's switch to a pen over here, right? Suppose you have a big list of numbers. Let me make this a bit less wide. Okay. And now you're going to take your list, right? And then you're going to split this into two parts. Okay. And then oops. Let me draw this a bit smaller so that it looks. Yeah. And then you're going to find the maximum, and then let me just call that big M1, okay? And the second value, let me call that M1, okay? And then here you're going to find the maximum value, M2, right? And the second maximum value, M2. Okay, so suppose you've done this using divide and conquer, okay? So you start with n numbers, right? You divide these into two parts. And then you find the max and the second max in the first n over 2 numbers, and then you do the same thing for the other n over 2 numbers. Okay. Now you have these four numbers. So what do we do with these four numbers now? Right. So we want to use these four numbers to get the max of the overall list of n numbers. Okay. So so we need to do some additional comparisons. Right. What should we do? All right, well, I mean, the overall max is going to be the larger of this big M1 and big M2, right? I mean, it's definitely, or actually, so we need to do, yeah, so here are the comparisons that we need to do. So we need to, oh, actually, I guess we can just compare, yeah, so actually we should just compare little m1, construct a comparison tree. Two nodes in level 1 are the okay. So Dehong, I'll get to your solution in a second. Okay, so let me just finish up with the divide and conquer thing. Okay, so what you should do first of all is you should compare M1 with M2, right? And then also you should compare M2 with M1. Okay, so if you do this, right, then yeah. So let's see. If M1 is larger, so suppose you know this, okay? If little m1 is larger than m2, then what are the max and the second max? If little m1 is bigger than big m2. Yeah, exactly, right? Yeah, because we already know that big M2 is larger than little m2, right? And then so therefore we know that the max and second max are just big M1 and little m1, okay? And then if, let's see, if, what about the other way? Okay, suppose m1 is less than m2, okay? A little m1 is less than big m2, okay? Then what are the max and the second max? Yeah, right. Then all we know is that, so we know something like, you know, we have M1 and M2, and then we have like little m1 here is going to be less than m2, right, less than m2, okay. However, we don't know which of big M1 and big M2 is larger. So therefore, you have to do an additional comparison in that case, okay. Yeah, so sorry about that. You actually do not want to compare little m2. So if this is the case, right, then you need to do another comparison between big M1 and then big M2. Okay, yeah. And so in total, if you do this divide and conquer approach, right, then you're going to have to do a comparison here, right, and then depending on the outcome, you might have to do a second comparison. Okay, so so therefore, altogether, you can write the complexity of this algorithm is something like, if you have a list of size n, then if the complexity is f of n, right, then we're going to divide this into two parts. So therefore, we're going to have like 2 times f of n divided by 2, right? And then plus, you have these 2 additional comparisons that you have to do to combine these 2 parts. Okay, so then, so we have this recursion for the complexity. And so I'm not going to ask you guys to solve this, but I'll just tell you that the solution to this recurrence is going to be something like 3/2 n minus 2. Okay, so this algorithm is going to take this amount of time to find the max and the second max. Okay, now I want to mention that there's actually a more efficient algorithm that I think De Hong was talking about. Okay, and so this algorithm is based on let's see. Well, it actually does. Okay, but you have to do something on top of the comparison tree. Okay, so let me just start with what you're saying, which is this comparison tree. Okay, so the way this works is if you have a bunch of numbers. Okay, so you have like x1, x2, x3, x4, and so on. Okay, up to like xn. Right. So you're going to form this comparison tree, meaning that you're going to first of all pair up these numbers. Okay, and then you're going to compare these pairs of numbers. Okay. And then whichever one is larger from each pair, right, you're going to have this pair, that number move up the tree, okay, and do another comparison. So for example, if between x1 and x2, let's say x1 is larger, okay, then x1 is going to move up a level in the tree, and then x2, you're just going to ignore x2 from now on, because you know x2 is not the maximum value, okay, because it's already lost to x1, okay. And likewise, for x3, x4, you're going to have one of these things move up a layer. Okay, so let's say x4. Okay, right. And then so this way, you're eventually going to form this this tournament tree. Okay, and one of these values is going to come out to be like champion in this tournament tree. Okay, it's going to beat all of the other values that it was compared to. All right, so let's say that x1 ended up beating all the other values. So then what you know is that x1 is the maximum value, okay? Because x1 beats all of these other values, and these other values, right? So for example, when x1 beat x4, then you also know that x1 is larger than x3, because x4 is already larger than x3, okay? So the fact that x1 came out on top means that x1 is the max. Okay, now the thing is that you also need to find the second max, okay? And the second max, what you can show is that the second max is going to be one of these values that competed against x1, but lost to x1. Okay, so for example, the second max it might have been x2, right? Because if x2 was actually the second max, then as soon as it got compared to x1, it lost, and so we stopped processing x2. Okay, but it's possible that x2 is the second max. Okay, likewise, it's possible that x4 is the second max. Okay, so x4 also competed against x1 at this node over here. Okay, so in fact, you have to look at all of these nodes that competed against x1 and then lost to x1 at some point. Okay, so here you have like x something. Okay, let's say xn. Okay, and now the second max has to be one of these values. Okay, so you can think about that, right? Because, right, yeah, so the second max is one of these values. And now, how many such values are there, right? So if you have, let's say you have n values, and let's say that n happens to be a power of 2, okay? So it's 2 to the h for some h, right? Then there are exactly h of these values that x1 competed against, okay? And you know that the second max is going to be one of these values. And so what you do is you take all of these values, right, and then you just look for the maximum value among this set of values. So you look for the maximum among like x2, x4, all the way up to xn, okay, whatever these values are, right? And so since there are going to be h of these values, right, because we have n values overall, and then this is a complete binary tree, so it's going to have height h. Okay, so there are h of these values, and you need to find the maximum one of them. So that's going to take you h minus 1 comparisons to find the second max. Okay, And that's on top of all the comparisons we did to find the maximum value, which is x1. Okay, and then there you can, if you just count up like how many comparisons you did. Okay, so these are all of these internal nodes in the tournament tree, right? And they're going to be m minus 1 of those nodes. Okay, so the total number of comparisons is going to be m minus 1 plus h minus 1. And here, h is going to be equal to log of n. Okay, log base 2 of n. Okay, so in general, it's actually going to be the ceiling of this. Okay, so the number of comparisons you need to do is going to be equal to n plus, it's going to be the ceiling of log base 2 of n, okay, minus 2. Okay, so that's an algorithm to find both the max and the second max. It's more efficient than the divide and conquer algorithm, right? Because that took something like 3/2 n. Okay, and now it turns out that this complexity, okay, this is the optimal complexity. Okay, so you guys can we don't really have time right now to go through that lower bound, but you can sort of look for some material that shows that this is actually the optimal complexity to find the second max. Okay, any questions about this algorithm? All right, so why don't we take a short break at this point? Let's take a break until let's say 1:45, okay? And then we'll come back and then we'll do the rest of this lecture together. Okay, yeah, so see you guys in a few minutes.